I wanted to share with you some of the experience I had in 3D printing, and actually for some of you can see some of the objects here that I printed, some of them a long time ago and some of them recently. There are many other people doing 3D printing, but what I wanted to expose today is some of the issues about 3D printing and maybe get you interested in building some models with Mathematica that you can print yourself. My background, I've always been interested, of course, in computers, and I was interested in the 90s in starting the process of figuring out how to extract objects from the things we were doing in computers at that time. And so in 1999, I built a machine to score glass. So it's actually a 3D CNC machine to score glass that still works to this day very well. It doesn't break the glass because you have to then break the glass by hand, but at least it scores. You can make any shape you want. It's a very interesting process. Behind that, I built a 5-axis CNC machine that I've used to create mold and things like that. Very interesting experience. But at that time was the beginning of the 3D printers, and when I saw what I could start to do with the 3D printers, I said that CNC stuff is very complex, very hard to do. It's so much more fun to use 3D printing. So I started to work with 3D printers. At that time, I was working at EA on a project that was starting called Spore, which became a large game for Electronic Arts. And then we started to go through figuring out how to print the creatures that people made in the game on those printers. And that's about at that time that we printed the first spiky. So you've seen, so this sculpture was actually made polygon by hand, and it was created at the beginning to be printed on this 5-axis CNC machine. So I actually built a version of this in wood that was created by the CNC machine from one piece at a time, and then assembled and glued together, and then I printed it on a 3D printer and was way much faster. Zico is a company that created 3D printers very, very cheap. And they changed the marketplace. The printers before that, the 3D printers before that were costing north of $100,000. And Zico started to provide printers at about $30,000. And the whole marketplace shifted to that price point very quickly. And I was able to get a Dimension ABS printer, which prints plastic like this. This is a model that was printed a few weeks ago. And the advantage of that, there are several advantages. One is it's actually less trouble to print, but also it has very good mechanical properties. And so I was running a robotic startups 4 years ago for a couple of years where we were building toys, robotic toys, and every day we would print a new model. And we could use it and put motors in it and then gears and animate the model. Because the properties of the printers were good enough and strong enough to make it immediately useful. I'll show you some of the examples of what it looks like. But now it's even easier. You have ProMetal and Shapeways. There are web services. If you search for 3D printers on the web for web service, printing services, you can just build a model, upload it to the website. They tell you if it works or not. If it works, they will print it for you, send it back to you. You just have to provide a check. Actually, I can give you some ideas of prices. This, because it's pretty heavy, I think was about $400 to $500 to print one of those. I have some metallic ones here that were cheaper. And another thing is now they print in glass. So this actually is sculpture is the upper surface that was printed in its glass. So don't drop it. And they have new materials coming all the time. So just to explain a little bit more the way 3D printing mostly works for most printers, there are only so many processes. The very first process that was invented is about epoxy. So it's you make a liquid epoxy, and with a laser, you paint something at the surface. And the surface of the epoxy will become hard very quickly. And then you drop it by hundredths of a millimeter or something like that, and you make a wave to wet the top of that surface again. And then you paint again with the laser the next level. And you do that 100 times, and you have 1 millimeter of volume. And it keeps going down like this, and you can build very large objects this way. And that, to this day, is still the most precise 3D printing process. All the others actually work in different ways, but they're more coarse. That one can be extremely precise, and those machines cost $500,000 to $1 million. Those lithography machines. So that's process number one. Process number two is something close to what Zico does, which is you have grains, you have plaster or something like that, and somehow you're going to wet the grains in the right place. So the way Zico does it is that they have a printer head, like an inkjet printer, and then they have also a layer of plaster. They wet it in the right place, and then with a knife, they bring another layer of plaster on it, and then print again on it, and wet it, and then they lower it, and then with a knife they bring another small layer of particles. So that's principle number two, which is used by many things, and that's how they do the metal plates. And rather than being plaster, they bring little balls of brass, and the laser will paint on them and glue them together, and at the end they can just keep the brass that has been sintered together. The third layer is what we see here. Is the third process is a system by which a hot gun pretty much will deliver a hair-like amount of plastic in specific positions. And what we see in general here, and you see that actually there's what's called the model and the support. There'll be two guns, and then the guns, one gun will be, in this case, the white material, and here the brown material that you see here. And the support is actually not plastic, it's sugar. It's a sugar-based solution. And then you see actually one of the things I was showing you here has been, it's this one, I think, was looking like that when it came out. And then you put it in an acid bath. It's not a very strong acid, it's a weak acid, but you put it in it, and the sugar dissolves. And then you're left with this. And you'd better clean it also because it will be acidic for a while. So, like I said, there's more and more materials. Wax is used tremendously. So this process with wax is used very much because they create jewelry with this. Because with the wax, they have very, very high quality of surface. And then they can put it they separate the two waxes, so they have two waxes that melt at different temperatures, so they just keep the objects they want to have, for example, a ring. So they'll make a special 3D ring, and then they will put that ring into refractory plaster, and then they'll be able to put gold in it. So that's used by jewelry. Wax is very much used. Paper, there's even somebody in Japan has built a 3D printer that is a cutter that moves, cuts paper, and accumulates that paper slide by slide, and at the end you have a 3D object using paper. I really don't think anybody's using that anymore, but 15 years ago it was pretty interesting. One common part of the process to all the different systems is that they start from a 3D object and it's being sliced. No matter what, at the moment, all the processes in the end require a small slice of the object. And so that has some big consequences on how you have to build it, because not only does it need to slice the object, but once it has a section of the object, it needs to know what's inside and what's outside, because it will only put stuff inside. And so it needs to be mathematically, it needs to be capable of knowing the inside from the outside of the mesh. And that's what makes things a little more complex. That's where the fun is. So one question people ask me often is why use Mathematica rather than 3D editors? So there are a lot of very high-level, complex editors that unfortunately I know too well, like Autodesk Inventor, SolidWorks. They are very high-end for the CAD industry, and also in the game industry we use Maya, Autodesk Studio, a lot of other Blender, a lot of other programs, and they are really great at creating graphics and shapes like that, but in fact, there's nothing wrong with using something like Autodesk Inventor or SolidWorks to create objects to print in 3D. They are very good at it. They do it very, very well. But the category of things I was interested in printing in the 3D printers were things that had a high number of parameters that I want to change. And those things are hell when you start to try to change the geometry, or if you try to do spiky in SolidWorks, it's not fun at all, because it's just not set up to do that kind of things. They're really good at extruding and doing the normal operations that you would use in mechanics, but they are not very good at creating things that have a high level of variation like we might want to do with mathematical objects. Another reason why I like to use Mathematica is because I want to solve the problem in the highest level language possible. And if you end up programming Autodesk Inventor, you're going to end up spending your day in C#, and it's kind of, I've done it. It's a little bit of fun, but I'd rather do it in Mathematica. The good news is Mathematica, for a long time, since version 4, I think, started to export STL reasonably well, and since version 6, it exports very good, very good STL files, so that makes things very, very interesting. Every time I describe what I do with this to some of my friends, they always ask, well, why don't you just figure out the function and have, Mathematica just do it for you? And I've tried. I've only succeeded for this one, actually. This one is a nice parametric plot 3D. So that one is easy. The others have not been able to. And it's because it gets too complex too quickly. And then in the end, even contour plot could not print it because your function would be so complex that evaluating one point will take several seconds, and then you'll never get any kind of resolution. But I think there's more hope about constructive solid geometry, so I've been begging for that for a while. And I think that those tools about managing constructive solid geometry are well understood by the computer science graphic industry, and there's no reason for not having them in Mathematica, except maybe time and money. So I hope we get, and that's an example of what you can get here if you, for people who are not familiar with constructive solid geometry, but you take this and end them, that gives you this, and then on the other side you take those cylinders, end them, but subtract them, and then you end up with something like this. And in the end, that's what you do when you want to do 3D editors, or when you want to create spiky. You start with a cone, and you want to remove a cone, and you want to remove some intersections, and you want to reassemble the whole thing. And that should be easy to do, but it's a little more complex. So what are the issues about 3D printing? Well, I've described the fact that the geometry, when we cut the sections, needs to always give us the interior of the model, and that's called being watertight. And also there needs to be some conventions on what's inside and the outside, and you need to have every polygon in the model follow that convention. So that's kind of a computer science problem. Another problem there is more a material science problem. So it turns out that the granularity of the material is impacting what you can do, and that the fact that there are layers is also problematic. So a defect on this one, which is very common, is that one of the spike here is missing its tip, and it's because it's the spike that was at the bottom here. And so the problem is that those layers, they have to attach to one another. And so there was nothing to start it well at the beginning. So it started with one dot, and then on that dot it had to put like 4 dots on the next layer, while those 4 dots they didn't hold, and so it failed there. And so sometimes you have to change the model and put something so that it can start properly and increase the probability of success of the beginning of a layer. So the larger the layer, the more likely it's going to start properly. And strangely, and I only discovered this through doing it over the years, the brain has some limitations. So nobody discussed that in terms of 3D graphics, but there are 2 things. The first one is, you're familiar with all the optical illusions about the fact that we cannot read an absolute color value or gray value. I mean, it makes fantastic tricks. You look at a gray rectangle there, and then you look at there and it looks black, and here it looks white. In fact, it's the same gray. Well, we don't have an absolute sense of scale. We just, we have to compare with something else to get a sense of scale. And it's a big problem when you spend your time looking at 3D graphics on the computer, is that you forget that the thing that you're working on is a sub-millimeter something that's completely useless for you to work on because nobody will ever see it, in if you're making a game, or if you work on something here, you just, it will be one dot, or it will be smaller than a layer. But you could spend days trying to put more features there. It's just that, if you're looking at it, you need something to constantly remind you of that reference. And so it's a problem I see when we make games, as I said, people spend time on details that cannot possibly be visible. And on creating 3D printing objects, the problem is slightly different, which is you think you're doing something like this, and you're looking at it, and it kind of looks like this in your mind, but the fact is you've built this, which is way too thin. The materials cannot possibly hold. And when I printed this, I really thought it was going to come out looking that good, but it came out really, really badly because it's too thin. And I corrected it, and I did this one, which came also. I multiplied everything by 2, and it was still too thin. And it's after this one came out, I said, OK, now I'm going to make it really big. And I made this one. And another example, is that those cubes, which I'll show in details in a few minutes how they're made, I printed them smaller, and then the holes disappeared. And because the way the material goes down, there's a lot of variation, so it's kind of a melange of the granularity and the fact that it didn't have a good thing, a good sense of scale. But what's even more surprising is this. It took me a while to figure out what it is. And what it is that when you're looking at it on the computer screen, your brain has to do the 3D reconstruction. You work really hard. I mean, it's an intense activity to maintain in your head the understanding of what you see in that 2D environment that moves in a spatial way and everything. It's an intense thing. And it kills your creativity. You're just so absorbed into trying to understand what you see. And as human beings, we're much better at understanding something that we hold in our hands. The scale is better. We have a lot of more information about it. And then there are problems you're trying to solve on the computer that you can't figure it out. You print it, and in 3 minutes, it's obvious to everybody. And so that's a really interesting reason why I think we're going to do more and more 3D printing in the future, is because it works as a human activity. It's a better way for us to interact with our, what we create. So I just wanted to explain a little bit what it means to be watertight. So this looks like a normal polygon, that should be watertight. But it's not been laid out properly. So in fact, here there is one polygon here, and then 3 polygons here. So 1 polygon here, 1 there, and 1 there. And what's wrong here is that where that point is not shared by this polygon. And what will happen is that due to manipulations, there will be errors, or there is, because we use in the end real numbers, there is an error, and the error will do the equivalent of this. The point will move, and because that point is moving here, there is the potential for a leak here. And so you cannot have any of those structures anywhere in your model if you want to print in 3D. This is illegal. It's an illegal move. So the fix is to do what's here, which is even if there is an error here on the points, on the position of that point, it keeps watertight because you only connect the same points. Does that make sense? And so the good news is that that's what, in the end, graphics complex is made for in Mathematica, is that those points are not really, we're not giving the same points with different coordinates or the same coordinates all the time. We just have, we give each point only once, and then it's up to you to connect them properly. And that's where the fun is. Another thing is you look at this cube, which is the same as this one, but actually what I use is I use face form blue-red to make sure that my polygon orientations was correct in front of the polygon, and if you look under, it's wrong. So this polygon form, it looks like a cube, but in fact, it's an object that's not a solid from an STL point of view because there's two skins that are oriented in the same direction, so there's no inside. Okay, and so face form blue-red is kind of the #1 thing you're going to use if you do anything, because you spend your time looking at your at your object, making sure that every polygon is oriented in the proper direction. Some of the details of the printing process is that so the lithography that I described, the first one, the epoxy, the really cool one, is fantastic, and it does not survive time. Within 6 months, it will start to warp. It will change color. It will shrink locally because the UVs, unfortunately, continue to impact the epoxy after you have it. The plaster solidified by super glue, it's like the Zico printers. It's very coarse, and then it grows locally. So the problem is that the humidity of the part as you build it propagates in the plaster while you're printing and after you're printing, and so it kind of grows an extra skin. It doesn't change dimension overall too much. It will shrink later, but so it's very hard to maintain. You don't have a lot of precision. It would be nice for something like this, but if you try to do something precise, you're going to be frustrated. An ABS deposit, the challenge there is that they really, if you look at it with a microscope, you really see that it's a hair. They do everything with it's a little hair of plastic that's being deposited. And so you have a choice when you make a surface in 3D, is it going to use only one hair, or two, or three, but there's no number in between. So depending on what you've been putting in your 3D, you're going to get more or less a surface you have within the precision of one hair. So you have to make your surface a multiple of hair widths to have any chance that it will hold. I mean, one hair, it will not build. There's no chance that that thing will put it right enough above it. So it has to be at least 2 hair width. That's the minimum size it has. And it's kind of better if it's like between 4 and 5, because then it will put 1 hair on the inside, 1 hair on the outside, and the machine in the between will connect them like this and build a honeycomb structure that will be very strong. So you need to, unfortunately, understand all of that if you want to make your model resistant at the end. In glass, it's actually much closer to the plaster. So the problem we have with glass is purely, well, apart from the fact that it's glass and very breakable, it's more like the plaster. Here's another problem, which is glass has a tension surface that is very, very high. So you cannot curve it or make things sharp with it. It's all bubbly. So I wanted to give you an example of, hopefully I'll be able to. So those cubes, just to show in little details on how they were constructed. And so it started with reading NKS and seeing the pattern that, it's just 137-degree geometrical rotation and progression that Stephen had in his book. And so I actually made it with those little square lozenges that I thought they were more fun. And then actually did a Delaunay subdivision around those lozenges. And then I removed the dots in the middle. So remove what was in black at the beginning, and then actually duplicated it, and then connected all the little square here from one another. So we see it's like a honeycomb structure now. And everything here is connected the way I described it before in terms of watertight. So the polygons are properly set. And then if you add the edges here, and you do that on the 6th face of the cube, you get, if you do it one way, you get what I call the introverted cube. And if you do it the other way, you get the extroverted cube. So in the end, it's not very complex, but it looks kind of organic, and it looks like a cube, which is what I was trying to do here. Let me try to go to the next one. So this one is I was trying to, I successfully printed a Rubiks Cube that comes out of the printer. I put it in the acid, and it works. And it cannot be taken apart because it's all, it's in several pieces, but the pieces came out fully assembled. So this was a study to look at what do I need to do to make, what are the surfaces for the Rubiks Cube, and we kind of know that, we kind of see here that we need to have that rotation and that rotation. after you've done that, you say, it's a sphere. So those are kind of the pieces of the Rubik's Cube, the way you want to think about them on how they're supposed to move. And then there's a center part, and so the center part looks like that's one of the segments of the center part. And you can see here how I use the red and blue to know and make sure that all my polygons are calculated properly, and the math on that is not too bad. And so you put them all together, and you get the middle piece. And so what's interesting is that if you buy a real Rubik's Cube, they look the same, but they have screws here so that they can take them apart, or in fact, put them together, where here it's being printed fully in one block. And so now you can see I needed to have a hole. So this is a hole, that's why it's red, because you see something that's empty in the middle, and then it becomes that piece, which is the piece that sits on the top of and that's a section of it. You can see how it's working. And so now that's the piece in place above one of the 6 corners, or face. And then that's a side, and I'm showing this side because it's, if you want to see the details. So when I debug this, I need to have some color changes to make sure that I don't have any leaks or anything. So, and I removed a series of polygons in the middle so I could look through and make sure everything inside was correct and everything. And that's the corner. I'm going to try and make it smaller probably. And that's the corner piece, and watching the gap, because you need to have a proper gap in between, otherwise they'll be stuck together. And that's the corner piece with the... So the Rubik's Cube like this, it's been pretty painful to do with graphics complex and assembling them, and I had to figure out every subsurface and put them together. It'd be very trivial to do if we had solid, constructive solid geometry, because there's like 5 objects to intersect and just do it. Take this and not that. And that's the cube as it's been put together. And that's if you export this as an STL, it will print as a Rubik's Cube. And the last example I wanted to give was, so that's the original spiky here. And let me try to show it in 3D here with transparency. And then what I wanted to do is the problem with the spiky is that it's kind of nice, but it's almost, looks like a weapon almost. You see, it's not very friendly. You touch it, you just, you can hurt yourself very quickly. And so I was trying to figure out how am I going to make it more organic. And so the way to do this is I'm going to use, and that's what I'm showing in the next pictures here, is a process that we call skinning in computer graphics, which is we put a skeleton in the middle, and we attach things to the skeleton, and then we move the skeleton and get a different shape. So first of all, I subdivide all the triangles that you might have seen at the beginning, and then I attach a skeleton. So what you might not see here is that there's a line here, which is a skeleton, and the skeleton has different bones, one after another, which become smaller and smaller. And those spheres is the degree of influence of any of the bone. And so then I actually rebuild the spiky with all those bones, and those bones here are moved. So it's kind of, it's as if spiky had a skeleton, and that was the skeleton, and you could see that the bones, rather than being straight up like they are like this, I've bended them in different directions. And then using that influence, the polygons have been modified. And so now you see a deformation. And so I didn't print it yet because I'm not happy about the way my bones are deforming. It looks like it's still a little scary. Yeah? We have not solved the scary part completely yet. I think that's all we can do today. That's it. If you have any questions, I'll be available.